Hi everyone and welcome to PrepFusion. Today we will start our lecture 3 of the this new next chapter, that is chapter 2, that is block diagram and signal flow graph. So in the previous chapter we learned what is a signal flow graph and how to draw it, how to draw it from a block diagram. So in this lecture we will do mainly solve questions of signal flow graph. Mainly what is solved using the block diagram method will solve using the signal flow graph here. Okay, so the first question we have already solved this previously. Here we have been given the block diagram. We have to find the transfer function of this system with the help of signal flow graph this time, right? So what I will first do is copy this block diagram and convert this into our SFG, right? So you also do the same. So first I will copy this, right? Then convert this. So what I will do is take this as a individual node, as this node, then this as node, and this as also node. Okay, I will take all of them as node. What I will do is first name them, right? So this is already a node, input node R, and this is already output node C, right? So I will name here this as M, this node as N, this node as O, and this node as P, right? And this is another node, output node, that is C. So what I will do, I will convert this into signal flow graph. So simply I will draw a straight line over here. Okay, then we have one M node over here, N node over here, then O node over here, and P node over here, and this is the output node, this is the input node, this is R. I will just write R and not bracket S. Okay, I'll just ignore it for now. So this is M and OP. Now from O to M we have one feedback, right? Negative feedback. So from O to M I have a negative feedback of minus H2. From O to P we have gained, that is another thing, but from P to H1 also we have another negative feedback. Okay, so that will be, okay, let me write this P in the bottom. From P to N, okay, just do it. From P to N we have another negative feedback of minus H1. Okay, so we have two feedbacks. Now let's write the flow equations, right? So this is one only, because from R to M we don't have any gain. Okay, from M to N we have only G1, right? From N to O, what do we have? We have G2 here, right? G2. From O to P we have G3. Okay, now solving this will be a bit tedious, so let's do it step by step. So firstly let me find the number of forward paths. So how many paths are there from input to output? So as you can see, I can go with the flow only here, right? This is also one. Okay, I can go with the flow from here to here. Can I move from here? No, this is against the flow, so I can't move from here, right? Can I move from here? No, this is against the flow, so I can't also move from here also. I can only move in this straight line, so number of forward path is only one. So equals to 1. Okay, so equals to N, right? So what is that forward path? That is R M N O P C. R M N O P C. Okay, so this is my forward path. Okay, so how can I write the formula? Mason's formula like is this one, right? This is K equals to 1 to N, which is summation of Pk delta K by delta, which is equals to P1 delta 1 by delta. Okay, so this is my forward path. This is the formula, right? So now what I will do is find the forward path gain. So what is P1 equals to? P1 simply is equals to this multiplication, right? So 1 times G1 times G2 times G3 times 1. So it is simply G1 G2 G3, right? So 1 times G1 times g2 times g3 times 1. Okay, so this is g1 g2 and g3. Okay, this is g1 g2 and g3. So now what is our loops, right? What is our loops? So this is the forward path. Okay, now let me find the loop gains of the whole system. Loop gains of the whole system. So L1, right? L1 is like, how many loops do we have? Let me copy this. So what I can say is, like, what is a loop? It follows a closed path, right? It comes back to that point again, that node again. So here what I can see, this is following this loop, right? This is following this loop. So this is one loop, okay, and this, right, this is also another loop. Okay, so we have two loops, this one and this one. So let me name this loop as L1, let me name this loop as L2. So just wait a second, too much sound. This as L1 and this as L2. Okay, so we have sorry, let me name this as L2 and L1. Doesn't matter anyways, so but still. Okay, L1 and L2. So what is the first loop? Like what is the path of the first loop? First loop path is, it's going from n going to O, then again coming back to M. Okay, so yeah, these last and first part will be repeated, right? So yeah, this is the path, right? So now what is the loop gain? So I am going from g1 g2 then minus h2 multiplied, right? So g1 times g2 times minus of h2. So the value of this is g1 g2 h2. Okay, g1 g2 h2. And what is L2? What is L2? So L2 is, again, what is the path of L2? It is n o p n, right? n o p n. Okay, so this is g2 g3 h1, right? g2 g3 h1, and we have minus h1 also. So we'll write this directly right now. g2 g3 h1, we have minus also, so minus will come here. Okay, minus will come here. g2 g3 h1. Okay, so now what we have to find, as we have two loops, right? I have to again check for number of two non-touching loops. Like, are there any combination of loops they are not touching, that is, their nodes are not common. Okay, but here I can see that these two nodes, right, O and N, are common. So number of two non-touching loops is 0. So hence we'll directly write delta equals to 1 minus this L1 plus L2. Okay, summation of the loop gains, right? That was in the formula. So plus 0, as number of two non-touching loops are 0, like there aren't any non-touching loops, okay, present. So what will be the value? 1 plus this becomes g1 g2 h2, g1 g2 h2 plus g2 g3 h1. Okay, plus g2 g3 h1. Okay, so this is the two non-touching loops. So now what I will do is find that delta 1, right? So associated path factor. Okay, I would find non-isolated loops. So what I will do, I will simply copy this, okay, and remove the forward path. So make this smaller. Now if I remove the forward path, right, do I have any loops present? No, because the nodes for these loops are gone, right? They are just floating, right? There aren't any nodes. Okay, so like delta 1 will be 1 minus 0, so it is 1 only. Okay, as there aren't any isolated loops present. So what will be my C by R value? simply what was my forward gain? It was P1, right? And what is P1? P1 is G1, G2, G3. So P1 is G1, G2, G3. Let me just check 1 second. Is it recording? Yeah, it is recording. G1, G2, G3. Now we have delta times 1. This is because this is 1 minus 0 only 1, and we have delta. What is delta? Delta is 1 plus G1, G2, H2 plus G2, G3, H1. So what does this become? This becomes this only. Okay, I don't need to write it here again. This only, right? This only. So this is my answer. Okay, so yeah, this becomes this. Okay, so this is our transfer function for this. Now check from that previous example from the block diagram methods, is are we getting the same one or not. So now let's come back to another question. So this question is given as the block diagram of a system is shown. Again we have to find the transfer function C by R. Again what I will do is first name the nodes, okay, then convert it into SFG, then find the equivalent answer. Now what I will do is do it a bit quickly here. Okay, so first what I will do is name the nodes, right? So again I will name them here. So this adder I can name it as M, N, then here as O, P. Okay, I'm naming all of them as differently just to be on the safer side so that I don't make any mistakes. Okay, so yeah, so now let me convert this, write the SFG, draw the SFG for this one. So we have input and output. So what do you have? M, N, O, P and Q, right? P and Q are really similar, just 1 multiplied with that, right? Because just after the adder it is, so 1 and 1. So let me name this. This is okay, this is M, this is N, and okay, I forgot to name another point here actually. So yeah, this is actually another point. This is actually O, this is P, this is Q. Okay, so what I can do is like Q and this one is same only, right? So I can ignore this also after this. So if you want, you can draw another like a node, or you can draw this same also. Okay, so yeah, I'm not doing it right now. Okay, so MN, this is O. Okay, O is a bit farther also. This is P, this is Q. Okay, so I will draw the feedback paths now. So where are the feedbacks going to? So P is going to M, okay, with gain as minus H2 because there is negative feedback. So minus H only. This is the path, right? P to M. Now this Q is going to O, so Q to O also. So what, how I'll draw this is like this one only. Q to O. I will just delete this slightly here. Okay, this is like this, Q to O. Okay, and what is this Q to O? Q to O is simply what is the gain? Gain is 1 only, but this is negative feedback this time, so this will be minus 1. Okay, just remember the gain is here 1, okay, but it is negative, right? So it will be minus 1. And from O to Q we are also going, from O to Q also we are going, right? Sorry, this one is N actually, this one is N actually. So that was the confusion here. So we'll go from Q to N. Okay, Just be careful about all these things, okay? Don't make a mistakes. Q to N. To delete this part. So yeah, this is N Q to N, and now where this is going. So yeah, from O to Q we are going with gain G3, and this is getting added up. So this time, right, this time we will just simply add O to Q. Okay, gain is G3, gain is G3. Okay, so this is getting added up from, okay, any other, yeah, we have only three feedbacks, right? So all those are covered right now. So let me write the flow gains, right? Okay, excuse me for my hair. Okay, so flow gains, this is 1, this is G1, this is what, from N to O is 1 only, right? From O to P we have G2 gain, G2. From P to Q only 1, Q to C also only 1. Okay, and yeah, all the gains are written. From M to N we have G1, already written that. Okay, so yeah, the signal flow graph is ready. Now let's find the number of forward paths. So yeah, I can see this one is a forward path, right, from R to C. Is there any other? This one, no, we are going against the flow. This one, no, we are going against the flow. But this one, is this the forward path? Yes. So I can go from here to here also, right? So in this case we have two forward paths. So number of forward paths equals to 2. Okay, so this is so what is one, first one, R M N O P Q C, R M N O P Q C. What is the another one? R M N O Q C. OQC. Okay, RMN OQC. So this is another forward path gain. So what will our Mason's gain formula look like this time? This will look like P1 delta 1 plus P2 delta 2 divided by delta. Okay, so I am writing this directly now. So what is the first forward path? So what is P1 equals to? So P1, right, we are going from here to here. So what path do I cover? I cover 1 times G1 times 1 times G2 times 1 1. So G1 times G2 simply is the forward path gain for the first loop, right? So this is the first one. Okay, I can write this as first one, and this is the second one, right? So what is the forward path gain for the second one? I'm not writing them explicitly, I'm doing this a bit quick faster this time. So for the second one, right, I'm going from 1 to G1 to 1, G3 to 1. So it's simply G1 times G3, right? So G1 times G3. Okay, so this is the second forward path. Now let's find the loop gains, right? Let's find the loop gains. How many loops do we have? So let me copy this. This is the one loop, right? This is one loop, and like this is also another loop. This is also another loop. Now do we have another loop? Okay, like I'm explaining you, like we're going from this point to this point. This is one loop, right? Now we're going from N to, again coming back here, this is two loops. Do we have another loop? Just check in this section, do we have another loop? So what I can see is, if I go from here to here, and then I can go here, right? I will have to go here, and yes, I'm coming back to that same point again. So this is also another loop. So this may seem a bit hidden to you, but this is also another loop, right? So basically we have three loops. Okay, we have 3 loops. So what is L1? What is L1? So let me name the first loop. Like this one is the first loop, right? This one is the second loop, and this one is the third loop. I'm not marking the points exactly. So L1 is simply we're going from this N, N to O to P Q, then again coming back to N. Okay, so what is the loop gain for this? So I'm going from this point, right? So 1 times G2 times 1 times minus 1, again coming back to the same point, so it is minus G2. So minus G2. Now what is L2? L2 is simply this one, right? This loop gain I'm considering it as L2. So yeah, let me name the correctly. So this is 1 only, this is 2 only. Okay, so this one is G1 times 1 times G2 minus H. So G1 G2 minus H, so minus G1 G2 H. So again let me name this M N O P, then again coming back to M. So this is equals to minus G1 G2 H, yeah, only H, right? Minus G1 G2 minus H, so G1 G2 minus H, right? And what is L3? What is L3? So what is L3? L3 is this one, right? L3 is L3 is this one, right? This one. So what is the like path of this loop? N O Q N. So N O Q N. So this is equals to 1 times G3 minus 1, so we get minus G3. So minus G3. So are there non-touching loops? Like are there nodes which are not common? So I can see N common in all of this, right? So there aren't any non-touching loops. Okay, so number of non-touching loops are 0, so I can directly find the determinant. Okay, like this common node also you can do find this in seconds, are there any non-touching loop or not. So delta equals to 1 minus G2 minus G1 G2 H minus G3, so it is equals to 1 plus G2 plus G1 G2 H plus G3. So this is what delta is equals to. Okay, so yeah, this is what delta is equals to. Now let's find the associated loop gain. So for delta let's find delta 1. Delta 1, what do I need to do? I need to remove this path, right? So again I will copy this, you don't need to write and remove that part. Like for you can directly solve it from the diagram itself. To explain it to you, so I have to like copy and paste all of these things, right? So for delta 1, right, what I will do, remove this path. So are there any loops present? So the nodes are gone, right? These nodes are floating now, so there aren't any loops present, so this will be 1 minus 0, so 1 only. Now for delta 2, it will be similar only. If I delete this, right, and if I delete this one, are there any loops present? No. For delta 2 also there aren't any loops present, so delta 2 equals to 1 minus 0, so it is 1 only. So now I can write the formula of the transfer function. So what was the formula? It was simply P1 delta 1 plus divided by delta. Okay, so what is C by R? What is C by R? So C by R is simply p1 delta 1. Okay, so what is p? What is p? P is p1 is g1 g2 and p2 is g1 g3. So g1 g2 plus g2 g3 divided by what is delta? Delta is 1 plus g2 plus g3 plus g1 g2 h. 1 plus g2 plus g3 plus g1 g2 h. So as you can see, like, even though it may seem like it took me a lot of time, but if we do it a bit fast, as you can see is that this takes much less time than what it took for us to use the block reduction diagram, right? So yeah, you can use this one for complicated block diagrams, right? G2 you can use this. Okay, this C by R. Okay, so yeah, let's move on to another question. So in the signal flow graph, find the gain C by R. Okay, what will the gain C by R? This is also a gate question, right? So the signal flow graph is already given. So what I will do, simply name the nodes, right? Name each nodes. This is M N O and this is P. Okay, this is M N O P. Okay, so how many number of forward paths do I see? I see one path from here to here. Here I can't see a path, but from here I can see a path, right? I can see a path. So number of forward paths is 2. So like this time I'll do this quickly. So n equals to 2. What are the two paths? R M N O P C and R M P C. Okay, these are the two paths. So how will our formula look like? C by R will be P1 delta 1 plus P2 delta 2 divided by delta I. So what is the forward gain? So from here I can do it directly. First path, so 1 times 2 times 3 times 4 times 1, so it is 4 factorial basically, which is 24, right? So what is P2? So P2 is right. P2 is simply this, right? This path. So it is 1 times 5 times 1. So it is simply 5. Okay. So these are our forward path gains. Now let's find the loop gain. So as you can see, I'm doing this a bit fast. Okay. What is my loop gain? So loop gain, right? Loop gain is how many loops do we have? We have this loop, this loop, this loop, these three. Do we have another loop? Do we have another loop? So from here to here, no, I can see. But if I go from here to here, then like this, right? We are going with the flow and coming back to the same point. So this is also another loop. So we have 4 number of individual loops. Okay. Four individual loops. Okay, so what will be our like loop gains, each of them? So let me take the write the loops, right? So this is M, N and M. Okay, so what do we write the loop side? So simply this is 2 times minus 1, so this is minus 2. Okay, now this is L2. Okay, L2 is N O and N. Okay, 3 minus 1, N O and N, so it is minus 3 only. Now what is L4 or L3? L3 is this one, right? O, P and O. This is minus 4 only, right? So minus 4, 4 times minus 1, minus 4 only, right? And this one, right? This one we're going from M to P to O, N, and then M. So M to P to O to N, then again M, right? So what is the gain for this one? What is the gain for this one? This is 5 times minus 1 times minus 1 times minus 1. So we are getting minus 1 at the end. So this is minus 5. Now, are there any non-touching loops? So are there any nodes which aren't common? So this node, right, this is common with all of them. So all of the nodes are present over here. But what I can see is this has M and M. This doesn't have any N or M. Okay, this is non-touching. Okay, but these two are touching because N is common. Okay, so and these two, right, O is common. So we have L1 and L3 are non-touching, right? So L1 and L3 are non-touching. Okay, as nodes are in common. You can check from diagram as well. This is the L1 and this is the L3. Are there any nodes in common? No, they aren't touching each other. Okay, they are away from each other. They aren't touching each other, right? There aren't any nodes in common. From that, there you can also understand. From here also you can understand. There aren't any common nodes. Okay, so now that formula will come into handy. So our L13, right, it will be the product of two loops. If we had another pair, that would have been added with this whole formula, but we have only two loops, right? So this will be, what will this become? So L1 is minus 2. Remember at the formula there was product, right? Summation of products. So each pair will get multiplied. Okay, these two are non-touching. Then if another pair was there which were non-touching, that would have gotten added. Where I will show you. And this L3, right? L3 is minus 4. So this is 8. This is 8. So what is delta equals to? Delta equals to 1 minus the individual loops, summation of the individual loops, which is minus 2, minus 3, minus 4 and minus 5. Minus 2, minus 3, minus 4 and minus 5. And this is plus, we have plus sign, plus 8. And if there were more non-touching loops, we would have added with there, then close the bracket, and then we would have searched for three non-touching loops, right? And multiple of those. But generally up until 2, that's the maximum we get. After this all of them are 0 only. So plus 0 only, we don't have any other. So what is the summation? This is 5, 9 and 14. 14 plus 8 is 22. 22 plus 1 is 23. So what will be our formula? Now we have to find the associated loop gain. So first let me copy this one. Now for associated, right, I will just remove the forward path. Okay, the first forward path is this one. Remove this one. So are there any loops present? No loops are present, right? So delta 1 equals to 1 minus 0, which is 1. Now let me take the second forward path this time. This will be 0. So again, like are there any loops present here? Can I see any loops? Yes, there is one loop, right? This one is the loop that is remaining. This one is the isolated loop. Okay, this one is the last man standing basically. So yeah, this is the loop present. So we have finally we have one isolated loop. So delta 2, right? So we have one isolated loop. How can I write it? So I will write this as this was the L2, right? So L2 dash I will write, because this is isolated from the others. So L2 dash equals to 3 times minus 1, the loop gain, basically minus 3, delta 1, like if we have only one loop, right? So we have only one loop, so there can't be a non-touching pair of loops, right? Because we have only one loop. So 1 minus 3, which is 4 only, right? So finally we have got a isolated loop. Now let us put everything into the formula C by R. So what is P1 equals to? P1 equals to, from what I remember, is 24 only. 24 and 5. So this is 24 times 1 only, because that associated loop gain was 1, plus P2 is 5 only, times the delta 2. What is delta 2? Delta 2 is this 4, right? Sorry, this is actually delta 2. Sorry, this is delta 1. Delta 1 was 1 only, 4 only. And what is R? R is sorry, what is delta? Delta is 23, right? We found out delta is 23. So our answer will be simply 44 by 23. Now calculate this and you will get your answer, right? Simply get your answer. Okay, a call is coming, so I will restart this. Like, just hold on a second, okay? Yeah, sorry for the interruption actually. So let's start with the next question. So again, we have been given a signal flow graph of the figure like this. We have to find the transfer function C of S by R of S. So how will I find the transfer function? Again, like I will copy this SFG first, and this is a gate EC question, right? So I copy this. Now what I can observe here is that we have one simple forward path from this R to C. So R times 1 times 1. Oh, this is actually 1 also. Okay, forgot to write 1 over here. This is also 1. R times 1 will be simply equal to C, right? So you can say that C of S will be simply equals to 1 times R, like 1 times 1 times R of S. So our question is simply over, right? Yes, no. Okay, this is wrong. Okay, why? Because we have another node incoming at this point, right? So we can't just simply write this. The flow equation is wrong because there is another node coming into this node, right? So the flow equation is wrong due to this node, due to this branch. Basically this branch is also incoming to this node. Okay, so incoming branch. So now let's do our convention method, right? What we used to do. Okay, first let us name the nodes. So this is M, N, O and P. Okay, M, N, O, P. This is C and this is R only. So how many forward paths we have? So I see one forward path here. Now if I try to go through here, right, I have to again pass through here. If I get back somehow, I have to again pass through here. So like non-repeated nodes are 1 only, so only we have one forward path, right? Else I can't, like I can come back here again, I'm repeating this node N, node M. Okay, so this isn't a forward path. Or I can go like there again, I'm repeating this node O. I've already passed through this. I can't again pass through this node. Okay, so we have only one forward path. Okay, so that thing is correct. So what will be our formula become? So N equals to 1, so C by R equals to P1 delta 1 by delta. Okay, now let me write the forward path. Basically color this to a different color. This is 1, okay, and this is also 1. This is R, this is C. Okay, this is C of S, this is R of S. Okay, so what is the forward path gain? It is P1 equals to 1 times 1, which is 1. So I hope you are understanding why there is only one forward path. Now let us find the loop gain, that is the determinant of this whole SFG, right? So how many number of loops we have? Let's see. So let me copy this again. Oh no. So one loop I can see here only, right? One loop I can see here only. Okay, another loop is this only, right? Another loop is this only. Now do we have any other loop? So I can go like this, but again no, I'm covering this again. So this loop, this isn't a correct loop, right? So we have only 3 loops in this, right? 3 loops in this. So this is one loop. Okay, let me name this as L1. Let me name this as L2. Okay, L1, L2, and this as L3, right? L1, L2, and L3. Okay, so these are the individual loops. Are there any non-touching loops? I think they are, right? Like whenever you see loops further away from each other, you will find them non-touching, right? So this loop and this loop are further away from each other. So also they don't have any common nodes. So the pair of them are non-touching. But this loop and this loop is touching with this one, and this loop also is touching with this one. Basically, they have common nodes. Okay, so first let me write the individual loops, then I will write the pair of loops, right? Like 2 non-touching loops. So individual loops, right? So what are the individual loops? So basically individual loops are, first one is L1 is M N and then again M, right? So what is the gain from here? 1 by S, then minus times minus 2, and we reached our starting point. So 1 by S times minus 2 by S. So next once I will write a bit quicker. L2 is simply this N O P and then N again. So N O P and then N again, right? So this is L2. So now how I will write this is that basically this is going from here to here. So the gain is here 6 times 1 by S times minus 4. So minus 24 by S, minus 24 by S simply. Okay, now what is the L3? L3 is going from here to here, right? O, P and O. Okay, O, P and O. So the value of L3 is 1 by S times minus 3. So it is minus 3 by S. Minus 3 by S. Okay, so this is basically L3. Now let's do the non-touching loops. So non-touching loops are number of 2 non-touching loops equals to 1 only, right? That is basically this loop and this one. So L1 and L3. So L1 and 3 is the product of those two, which is basically this one is minus 2 by S. Sorry for the noise outside. Minus 2 by S times this minus 3 by S, right? It becomes 6 by S square. Okay, so now what is the determinant basically? So the determinant of this S of G, right, is 1 minus 2 by S minus 24 by S minus 3 by S plus 6 by S square. This is basically 1 plus 29 by S plus 6 by S square. Okay, now let us find the associated loop gain factor, right? So delta 1, right? What will be delta 1? Again let me paste the SFG. What I will do is remove the forward path gain this time. Okay, remove the forward path. So do we have any loops present? Yes, we have 2 loops present. One is this one, right? This loop and this one. So basically the L2 and L3, both of them are present. Okay, so what will be the, we already know what is L2. So L2 is already minus 24 by s, and L3 is already minus 3 by s. Are they non-touching? No, they aren't non-touching, right? They aren't non-touching. O is the common node, also P is also the common node. So basically what we will do is end this here and find delta 1, which is the associated loop gain factor. So 1 minus 24 by s minus 3 by s equals to 1 plus 27 by s. Okay, 1 plus 27 by s. So yeah, this is the associated loop gain factor for the like the case 1, right? So now let us find the expression for the transfer function C of s by R of s, which is equals to this loop path gain, that is 1 only, and the associated loop gain factor, that is 1 plus 27 by s, and the determinant of the SFG, which is 1 plus 29 by s, no, not s, it was s plus 6 by s square, 6 by s square. So C of s by R of s equals to simply multiplying a numerator and denominator by s square, s plus 27, okay, and this is s square plus 29s plus 6, right? So this is our basically answer for the question. Okay, so we'll go to the next question, but I think my recording storage is not there, so I will again pause the video, then like again restart. Okay, so just hang on for 1 second. Okay, sorry for the interruption. Let's start. So this is the next question. This is also a gate question basically. So what we have been given is like that we have to find the transfer function y upon R of s, and we have been given this block diagram. So simply what you can do is you can use reduction techniques here also, okay, but these are connected in parallel, right? You can subtract them also, but what you can do is use the SFG also, okay. So what we will do is use SFG, okay, and the homework for you is using simple equations. From there also you will find that it is more easier to solve with equations rather than simple SFG. So first I will solve this, like you stop the video and you solve it, okay, using equations, and I will solve again after, okay. So I will first solve with equations, then I will solve with SFG. So you will see the difference when to use equations and when to use SFG. So SFG is when the block diagram is very big, right? When the block diagram is very big, then use SFG. Here the block diagram is not that big, okay, it's small, so we can use simple equations, that method, right? Simple equation method, we don't need to use that block diagram, okay. So yeah, first let me use the method 1. So let me first draw the this block diagram, right? So this will take time. This is plus, this is minus, this is R of s, this is y of s, and this is simply 1 by s plus 1, and this is also 1 by s plus 1, okay. Let me write this properly. 1 by s plus 1, 1 by s plus 1, okay. So yeah, this is basically the block diagram. So now let's solve it. What I can see over here is, if I assume this as like x, right? Assume this point as x, okay. So what will happen? This is x times 1 by s plus 1, and this is also x times 1 by s plus 1, and this is getting subtracted. So here I have 0, right? Here I have 0, okay. So like what is x equals to? X equals to 0 only. X is equals to 0 only, right? Wait, let me like solve this equation like this. No, okay, no, what I see is this is x divided by s plus 1 minus x divided by s plus 1, okay. This is my here, this is my y, okay, which is equals to like 0 only, right? Which is equals to 0 only. So this is equals to like 0 only. So here I have 0, okay. Now this r comes over here, okay. So r equals to x of s. Now this r is getting multiplied with 1 plus s, and this is the y only. Okay, this is the y only. So y equals to this only. So y of s equals to x by s plus 1. So y, okay, let me write this in different color. Y of s by r of s equals to 1 by s plus 1. Rather simple. Okay, so you see like how simple this was. Okay, now if I solve it with SFG, this will go a bit lengthier than it is required really. Okay, so first what I have to do is draw the SFG, right? First I have to draw the SFG. So I will name the nodes. Okay, name this as M, this as N, this as O, okay, and this as P. Okay, naming the nodes like this. Now drawing the SFG. So we have one, okay, we have one node here actually, and we have another node here. Okay, so this is one node, this is one node, this is one node, and this is one node. Okay, and this is another branch, this is another branch, this is M, N, O, and P. This is another branch. Okay, and this is another branch, this is another branch, this is another branch, and this is another branch. So this is R of s, this is y of s, right? What is the gain from here? It is 1 only. Okay, simple line. Okay, and what is the gain from M to N? It is again 1 only, right? But here the gain is 1 by s plus 1. Here also the gain is 1. Here the gain is minus 1 by s plus 1, because we have a minus sign here, right? Minus sign here. Let me remove all this jargon. Okay, we have minus 1 by, here we have minus, right? That's why minus 1 by s plus 1. Okay, and we have 1 over here. Okay, that is basically the SFG, right? This is 1 also. So now how many number of forward path are there? So what I can see is this is the only forward path gain. Here I can't go from here, right? I can go from here. If I go from here, again I'm repeating my node. So we have only one forward path. So n equals to 1. Okay, so C by R equals to P1 delta 1 by delta, right? Now what is basically P1? P1 is this one, right? So this is 1 times 1 by s plus 1 times 1. So it is 1 by s plus 1 basically. Now what is delta 1? Now I will do this directly instead of writing individually. Okay, so you have to practice with me like that. So how many number of let's find the determinant first, the denominator. Loops are there. How many number of loops are there? Is this a loop? No, we are coming back from here, but this is a loop, right? This is a loop, correct? Okay, and is there any other loop? I can see this is a loop, but is there any other loop? Just check here, is there any other loop? What I can see is, if I go from here, I can go from here, I can come this side, then again complete the path. So yes, there is a loop here. So it is M and P M. Okay, there is a loop here, right? So I have two individual loops. Now are they non-touching? So this one, right? Obviously there is a common, right? This is only common. N and P are common. Okay, and this is, yeah, this is common. So obviously they aren't non-touching. So I can write this directly. So what I will write is first this loop, right? First this loop. So what is this loop? This is 1 times 1 by s plus 1 times 1 times 1. So this is basically, you have to practice writing this directly, because in gate exam you can't waste so much time. Now this is not minus, this is plus. Again this loop, right? This loop is minus 1 times minus 1 by s plus 1 times 1. So this is minus 1 by s plus 1. Okay, so yeah, this is basically what my determinant will be. There aren't any non-touching loops. Now if I remove the forward path, are there any loops left? No, obviously all the loops, right, have to follow this path. So if I remove this, then like there aren't any loops left, like individual isolated loops left. So what I will do is simply write here 1 minus 0. Okay, so I can from here directly write what is the transfer function. It is 1 by s plus 1, which is this wasn't c by r, this was actually y of s by r, y of s by r of s. So y of s by r of s equals to 1 by s plus 1, right? 1 by s plus 1. So yeah, this is basically the solution for this. Now you see which one suits you more, right? You see which one suits you more. So let's go to another question. So okay, we have so much space. This is the 12th question. So these are just different varieties of question to get you like accustomed with the level that gate gives. And the main thing in SFG, right, you have to find whether like what types of loops are present over there, right? So like is there an extra any other loop that you can't see, okay, that is hidden there? So that is the more important thing to notice here. Also for that isolated loop thing also, right? So you may find 2 loops, but there are actually 3 loops in that following SFG. So from there you may make a mistake in the question. So it is important to always keep in mind, like, am I missing any loops or something? Okay, that is the like most thing where students mostly make the mistakes, right? So yeah, that part is important. So again, we have given a signal flow graph, and we have to find the transfer function y of s by r of s, and this has come in GATE 2006. So again, the same procedure I will follow. Name the nodes, right? I will name the nodes. M N O P. So this is M N O P. Okay. Now, how many number of forward paths are there? I can like simple, this path is always there, right? Always there. So this is the one forward path. Is there any other forward path? So I can go from here, I can go from here, and yeah, I can complete the path, right? I can complete the path to output from input. So this is another forward path. So can I go from here? No, I can't go from here. Okay, there are only 2 forward paths. So n equals to n equals to 2. Okay, so y of s by r of s equals to simply p1 delta 1 plus p2 delta 2 divided by delta. Okay, so now slowly I will write this directly. Obviously here writing this directly is difficult because the loops are like number of loops are high, so writing this directly will be difficult, but still I will try. Okay, so first thing is, what is p1? So p1, right, p1 is this one only. So it is 1 times 1 by s times 1 by s times 1 by s times 1. So let me write like this: y upon one times 1 by s times 1 by s times 1 by s. Okay, and what is the delta 1? So delta 1 again, right, if I remove this, are there any loops present? No. Like if I remove this, right, so all these nodes are removed, so there won't be any like we can't find any loops, right? So this will be simply 1 minus 0. Okay, so this is how you can do this directly. Okay, but just be careful, if you aren't comfortable with it, obviously you do it slowly. Okay, that's the important part, but the answer should come as correct. Okay, so that is 0 only. So now what I will do is simply find the loop gain for the second path. So this one is 1 times 1 by s times 1. So this is simply 1 by s only. And are there any loops? I think there are, right? Because like this is going here. Okay, there are loops here also, because these 2 nodes are gone. So there is one loop here, there is one loop here, there is also another loop. Okay, like this one, but the nodes are gone, right? The nodes are gone. So this also has no isolated loop, right? No, generally that's the case. Okay, just be careful if there that isn't, but generally most cases, if I remove the forward path, we get 0 isolated loops, but 1 2 may come. Okay, so this is 1 minus 0. Now let's find the determinant of the SFG, right? So this is one loop and this is one loop. Okay, and I revealed to you like that loop is bit hidden. This is the other loop, right? Other loop. Okay, so sometimes you have to be just very careful, like how many loops are there. Okay, so this is like another loop, and they are not repeating, touching, not like nodes are not repeating, right? But all of them are touching, right? All of them are touching each other. They have common nodes. So the second term, non-touching loops, two non-touching loops will be 0, but the individual loops, there are 3 individual loops. So let me slowly write the each gain, like gain of each loops, right? 1 minus the first easier one, that is 1 by s times 1 by s times minus 1. So minus 1 by square, and this is 1 by s times 1 by s times minus 1. So this is again minus 1 by square, okay? And the third loop, right, this is minus 1 by s minus 1, so plus 1 by s times 1 by s, which is 1 by s square only, okay? So plus 1 by square. If you can't, if you aren't able to follow along, so you would do it like the previous questions, as I did it like slowly, okay? Break this down and solve it. So few things you have to do by yourself also, because in gate examination you will be solving the question, not me, okay? So you have to practice, right? I won't show you everything here, okay? You have to do it by yourself also. So y of s upon r of s equals to, this is simply 1 by s cube minus 1 by s 1 plus 1 by s square. So if I multiply s square on both sides, right, what do I get? So I get as simply, this is, I should multiply s cube, right? I should multiply s cube. So s cube, I can multiply, this becomes s square minus 1, and this becomes, okay, why is this minus 1? Actually this should be plus 1, right? Okay, yeah, this should be plus 1, sorry. See, these types of silly mistakes happen in gate examination also. This is plus 1, and this is s times s square plus 1, right? So what is the transfer function? Y of s upon r of s, it is equals to 1 by s, okay? So you can solve it in single page also, okay? In your examination you get a small rough book, you can solve in that in 2 pages, there in 2 pages also, but you have to know the concept, right? You have to do it fast also. So I am showing you both ways. I am solving it slowly, now I am solving it fast, okay? So so that you can understand, like in actual examination, how you should solve, okay? Initially you solve it slow, as I showed, like the whole process, right? But at certain stage you have to solve it very fast, okay? So this is that stage. I've already explained you 2 questions, 3 like many questions before this. So now I will solve this in a fast manner, but just be careful, like while you are solving in fast manner, you do not miss any loops. So that is the important part, right? You should not miss any loops. So again, we have been given a signal flow graph, and we have to find the transfer function, right? Again, like this, whenever big signal flow graphs come, right, just be careful of the loops. Are you missing any loops or not? And if very big signal flow graph comes, obviously solve it slowly, don't solve it very fast, okay? So yeah, this was the important part to note. So again, let me copy. We have to find the transfer function p of s upon n of s. So this is interesting part, right? So like it didn't ask us to find the transfer function c of s upon r of s. What is it asking us to find is p of s upon n of s. So what is p? P is here and n is here. So in signal flow graph, right, in signal flow graph we can find the transfer function between any 2 nodes, right? But the problem is, as I mentioned earlier, right, as I mentioned earlier, that we can't change the input, right? We can change the output. So I can take a node from here and make it p here, but I can't change the input. So how will I find the transfer function here? That will be very interesting. So let me first copy it. I will explain to you what I will do, right? So let me first copy this. So for p, what I will do, I will take one output from here, right? Take one output from here. So this I will name as p dash, and this I will name as p. So this is output, that is fine. But what about input? What I will do to this n, right? So for n, right, what I will do is I will do a bit of trick, okay? I will take an output from this n. I will name this as n dash, okay? Take one output from this n also, okay? Then find the transformation of n with the input r of s. Then what I will do is simply find the whole transfer function c of s upon this r of s, right? Then what I will do, I will multiply those two, and I will find the ratio of n dash upon R of s. Okay, so if I do that, then I will be able to find basically the ratio, right? Basically what I can say is this P, right? P is equal to C only. Okay, because P dash times C is like this C only, right? So if I find C upon this R of s, then I find N upon this R of s. Okay, then I take the ratio of those two, then R will get cancelled and I will be left with this P upon N, or P is equals to C only. So first thing what I have to write is P is equals to C. Okay, because like this P times 1 equals to C only. Okay, here I can see. So C of s equals to P of s times 1. So C of s equals to P of s, right? C of s equals to P of s. So one thing is fixed here. So now what is the next thing? I have to find two transformations. First one is basically C of s upon R of s, and okay, let me wait. I will find C of s upon R of s. Then I will take the ratio of simply this N of s, that is also output, upon R of s, and the R of s will get cancelled. Okay, we will be left with simply C of s upon N of s, right? And that is basically equals to P of s upon N of s. One more important thing to note is that like the in an SFG, right? In an SFG, the determinant will be same wherever the output we take from. Why? Because simply we just calculate the loop gains, right? The loop gains. So the delta will be same regardless of where we are taking the output from. Okay, so the individual loop gains may change. No, the associated loop gain may change, but the delta will remain same. So in an SFG, the delta will remain same. Delta will remain same regardless of where we take the output from. Okay, regardless of where we take the output from, the delta will remain same. So how will I reduce this, right? How will I reduce this? So I will now write this directly actually. So first is basically this C upon R, right? C upon R. So how to write this? So C upon R will be like, how many forward paths are there? I can see there are two forward paths, right? One is this one, okay, another is simply this one, right? So we have simply two forward path gains. So this one is 1 by s times 1 by s times 1 by s. So let me first write that actually. I'm writing for this one, right? C of s upon R of s. So 1 by s times 1 by s times 1 by s. Okay, now let me like write here C of s upon R of s. Now what is the associated loop gain? So if I remove this, right, if I remove this, will I be left with any loops? No, all these loops, right, will be gone. So I can simply write here is, let me recolor this actually. One minus 0. Now we have another forward path gain, right? So this is the other forward path gain. So the other forward path gain is 1 by s times minus 2 times 1. So basically minus 2 by s. Again, if I remove this, right, if I remove this forward path, so we will not be left with any loops because these nodes are common, right? These nodes are common, so we won't have any loops left. So this will again be 0. And delta, right, I won't calculate the delta, because the delta, if I take the ratio of these two transformations, the delta will anyways get cancelled. Okay, now what is N of s upon R of s? So N is n is here only, okay, and r is here. So if I go from here to here, so we have only one forward path. I can't go here and come back, because again this node will be repeated, okay. So only one forward path, that is 1 by s, okay, 1 by s. Now are there any loops? Yes, this time there are loops, like isolated loops, right? This one is an isolated loop, but these and these, all these are common to here. So this loop is only the isolated loop. So what I can do is, what is the forward path gain? It is 1 by s, right? Now what is the isolated loop gain? It is this one. This is 1 by s times minus 1, okay. So minus 1 by s. So yeah, this will be this will be simply minus 1 by s, right? So this is by delta. Now I will take the ratio of these two, right? Ratio of these two. So C of s I can write as P of s only, because C and P are, both of them are same. P of s upon R of s divided by N of s upon R of s equals to, the delta will get cancelled. What I will be left with is 1 by s cube minus 2 by s divided by 1 by s 1 plus 1 by s. So I will multiply like s cube, okay, on both sides. So like what I will be left with is simply 1 minus 2s square, okay, and I will multiply s here also. So this is s square only, so s square plus s, okay. So this will be simply my answer, right? This will be simply my answer, okay. So okay, am I doing everything correctly? Yeah, I'm doing everything correct only, right? So like the solution to this is this one. So I hope you understand, like if we have to find from a input node that isn't the actual input of the SFG, so we have to take the ratio of those two, so that the actual input gets cancelled and we get the desired transformation, okay, desired transformation, okay. So yeah, this is the like solution for this question. Now let's go for the okay, this is the end of this lecture, okay. This lecture has already gone very lengthy, so in the next lecture I will solve a few more questions, okay, and like teach you the limitations of SFG, right? Mason's gain formula. What are the limitations of Mason's gain formula, okay. So yeah, thank you for watching and see you in the next lecture.